It's 1:21 and no one has called in, so I'm going to continue to do problems and post them. Okay, so let's make sure we're recording. Yep. And here we go. Change the lighting just a little bit. Okay, so here we have the reaction of (750 grams each of ammonia and O2 was found to produce 562 grams of nitrogen monoxide. And here's the balanced reaction. What mass of water is produced by this reaction? So this is a limiting reactant type problem. And the way I'm going to tackle it is, since we want to know how much nitrogen monoxide we need to form, I'm going to take the mass of 750 grams of ammonia, find out how much nitrogen monoxide we can make, take the mass of 750 grams of oxygen, see how many grams of nitrogen monoxide we would make, and whichever one is the less, that's how much we would make. So here we go. The general outline is to take grams of A, turn that into moles of A, take moles of A, turn that into moles of B, and take moles of B and turn that into grams of B. Now, for grams of A to moles of A, we need the molar mass of A. For moles of B, A to moles of B, we need a balanced reaction. And for moles of B to grams of B, we need the molar mass of B. So I'm going to take my 750 grams of ammonia, and I'm going to turn that into moles of ammonia. Now, nitrogen has a molar mass of 14.01. Hydrogens are 3.03. You add that together, and you get 17.04. The mole ratio of ammonia to nitrogen monoxide is 4 moles of nitrogen monoxide to 4 moles of ammonia. The molar mass of nitrogen monoxide is 14.01 plus 16, which comes out to 30.01. So I'm going to estimate my answer so I make sure that I don't mess things up in my calculator. 17 goes into 30 about 2 times, but not quite. 4 divided by 4 is 1. 2 times 750 is 1,500, but it's going to be less than 1,500 because 17 does not go into 30 2 times. So I'm going to expect the answer to be maybe 1,400. And let's see what we get. $1,320. And we get 3 significant figures. So there we go. And that's grams of nitrogen monoxide. So that's the theoretical yield if we use 750 grams of ammonia and we have as much oxygen as we need. I'm going to do the same thing with oxygen. Now, the mole ratio is 5 moles of oxygen to 4 mole of NO. And then 30.01 grams of NO to 1 mole of NO. And I'm going to do my little estimating again. 30 divided by 32 is about 1. 4 out of 5 is about 1. So my answer over here is going to be a little less than 750 because I know this is a little less than 1 and this is a little less than 1. So maybe the answer is 600. Maybe it's 700 in that range. and I get 563 grams of NO. So there's enough oxygen to make 563 grams of NO, but there's not enough oxygen to make 1,320 grams of NO. So that means that this is the mass, 562 grams. They already gave it to us. Darn it. I just wasted my time. All right. So here I found, based on the NO, that the oxygen is the limiting reactant. So I'm going to use oxygen to figure out how much H2O I'm going to make. So I would take my 750 grams of oxygen times 1 mole of oxygen for 32.00 grams of oxygen times 6 mole of H2O per 5 mole of oxygen times 18.02 grams of H2O per 1 mole of H2O. And I'm going to estimate again. 18 will go into this almost 2 times. This is 1. So we basically have 750 divided by 2, which is about 325. Another way to do this, however, is I could have done this, that since I know that, well, actually, I can't do it that way. So I'm going to go ahead and multiply 750 times 6 times 18.02 divided by 32 and divided by 5. And I get 506 or 507 grams of H2O. Okay. I see my problem with my estimating. This is bigger than 1. So I got to divide this by 2 and multiply by a little more than 1. So half of this would be 375. You got to jump that up because of the 6/5 here. Okay. And that's A. What mass of O2 is required to consume 750 grams of NH3? So we can do this. 750 grams of NH3 times 1 mole of NH3 per 17.04 grams of NH3 times 4 mole of NH3 and 5 mole of O2, and then times 32.00 grams of O2 per 1 mole of O2. Estimating again, 17 goes into 32 about 2 times 5/4. I'm going to say 2. So it's going to be around 1,500. And let's see what we get. Well, kind of discombobulated the paper there. Okay, 750, and this should be 750 dot times 5 times 32 divided by 17.04 and divided by 4 gives me 1,760 grams of O2. So we could have actually used this to figure out that we don't have enough O2 to react all of the NH3. And if there's not enough O2, because we only have 750 grams, that means not all of the NH3 will react and some will be in excess. Okay, so there's that problem. Put that off to the side. And let's look at another problem. So we have here that iodine is made by the following reaction. So we have this sodium iodate reacting with sodium bisulfite. This is called bisulfite, or it's also called sodium hydrogen sulfite. Remember, SO4 is sulfate, so SO3 is sulfite. Now this combines to make sodium hydrogen sulfate, water, I can say water because it's a liquid, and iodine. Okay, name the two reactants. Actually, you know what, now that I see that, I believe this is one of the problems that is in the homework, so I'm going to skip this one now. You can look that one up in the homework solution. All right, this one I don't think I did in the homework. An Alka-Seltzer tablet contains exactly 100 grams. This should really read precisely, but your author does not like to use the word precisely. He likes to use the word exactly wrong. So this has 3 sig figs, precisely 100 milligrams of citric acid, plus some sodium bicarbonate. What mass of sodium bicarbonate is required to consume 100 grams of citric acid by the following reaction? So we're going to assume this is balanced, although you might want to check and make sure. So here we want to know for the 100 grams of milligrams of citric acid, what mass of sodium bicarbonate is required. Now, this is in milligrams, and that's going to make things a little tricky, but I'm going to show you a way to deal with it. I'm going to take my 100 milligrams of citric acid, H3C6H5O7, and I'm going to convert that to millimoles of citric acid. So this is millimoles of citric acid. So what is a millimole of citric acid? A millimole is a thousandth of a mole. So I'm going to take a thousandth of a gram and turn it into a thousandth of a mole. I'm going to turn this into millimoles of sodium bicarbonate. And then I'm going to turn this into milligrams of sodium bicarbonate. And when I get this in milligrams, it'll give me a sense of how much of the tablet is citric acid and how much of it is sodium bicarbonate. So I'm going to start off with my 100 milligrams of citric acid. And when I add up all the molar masses of the atoms, 3 hydrogens plus 5 more are 8.08 for the hydrogens. 6 carbons is going to be 72.06. And 7 oxygens is going to be 70 plus 42, which is 112. Add these all up together, and you get 14. Here you get 2. Here you get 9, and you get 192.14. Now, this 192.14 we usually think is not 192.14 grams equals 1 mole. But I can also say that 192.14 milligrams equals 1 millimole. So if I put a milli in front of the gram and a milli in front of the mole, I'm good to go. So I'm going to multiply this by 1 millimole of citric acid for 192.14 milligrams of citric acid. Okay, now from the balanced reaction, I have 1 millimole of citric acid. And I have 3 millimoles of sodium bicarbonate. Millimole sodium bicarbonate. Okay, now the molar mass of sodium bicarbonate is going to be 22.99 plus 1.01 plus 12.01 plus 48.00. So we know that's 60.01. Add these two together and you get 23 or 24. So 24 plus 60 is what? 84. 84.01 grams of sodium bicarbonate. And here I made a mistake. I don't want grams, I want milligrams per 1 millimole of sodium bicarbonate. So this is the same process as before, but instead of converting from moles to millimoles and so forth, or milligrams to grams and so forth and so on, I'm just keeping everything in millis. Okay, so I'm going to estimate the answer. This goes into this twice, but a little bit more. 2 goes into 3, like 1.2 times or 1.5 times. But I'm going to say this is a little bigger than 2, so it goes into that, we'll say 1.2 or 1.3 times. Times 100 is going to be like 130 or 120. So let's see what we get for our answer. 100 times 3 times 84.01 divided by 192.14, and we get 131 milligrams. Okay, and so there's your answer. And you can see that the mass of each is very similar to one another. So your tablet's probably about half sodium bicarbonate and half citric acid. Okay. Let's put this one off to the side. Let's take a look at this next problem. So in this problem, we're told that a non-carbonated soft drink contains an unknown amount of citric acid. If 100 milliliters of the soft drink requires 33.51 milliliters of 0.102 or 0.0102 molar sodium hydroxide to neutralize the citric acid completely, what mass of citric acid does the soft drink contain per 100 milliliters? The reaction of citric acid and sodium hydroxide is as follows. So here, what I'm going to do is I'm going to take my milliliters of sodium hydroxide and convert that into liters of sodium hydroxide. And the reason I'm doing that is because I know that with this concentration, I can convert from liters of sodium hydroxide to moles of sodium hydroxide. And the moles of sodium hydroxide will give me the moles of citric acid. And then the moles of citric acid will give me the mass of citric acid. So let's go ahead and start. We have 33.51 milliliters of sodium hydroxide times 1 liter of sodium hydroxide per 1,000 milliliters of sodium hydroxide. The concentration is 0.0102, 0.0102 moles of sodium hydroxide per 1 liter of sodium hydroxide. We know that the mole ratio is 3 moles of sodium hydroxide per 1 mole of citric acid. And we know that the molar mass of citric acid is 192.14 grams of citric acid. Per 1 mole of citric acid. So that's supposed to be a carbon right there. Boop, carbon. So I'm going to estimate my answer. 192 is really close to 200, which will go into 1,000 5 times. 5 will go into 33.51 about 6 times. 3 will go into 6 2 times, and 2 times this is 0.02. So the answer is 0.02 grams-ish. Let's see what we get. 33.51 times 0.0102 times 192.14 divided by 1,000, and then also divided by 3. And we get 0.02. Now we get 3 significant figures from this number right here. So 0.0219 grams of citric acid. And this is the kind of work we'd expect to see for a problem like this. Okay, so we're done with that one. We're going to move along. This one is a mass percent problem. So when we read through the whole problem, the last part is what is the mass percent of oxalic acid in the mixture? So that's where we want to start. We want to start with the mass percent is equal to the mass of oxalic acid, which is H2, C2O4, over the mass of the mixture times 100%. So remember, mass percent is the mass you're interested in divided by the mass total times 100%. Now, we know that this guy is 4.554 grams. So all we have to do is figure out the mass of the sodium or the oxalic acid. And now that I am doing this problem, I'm realizing, you know what? This is one that we did in the homework assignment, so you can find it there. So I'm going to move on, and I'm going to go to this problem. A solution of hydrochloric acid has a volume of 125 milliliters and a pH of 2.56. What mass of sodium bicarbonate must be added to completely consume the HCl? Well, for this one, we're going to need a reaction. So we've got hydrochloric acid plus sodium bicarbonate makes CO2 plus H2O. And remember, to make this, we need H2CO3. Here's one hydrogen, here's another hydrogen, and here's the CO3. And what's going to be left over is sodium chloride. So this is our balanced reaction. Now, we know that the hydrochloric acid has a volume of 125 milliliters. And we want to know what the mass is of sodium bicarbonate. So here I'm going to start at the end this time. So we want to know the grams of sodium bicarbonate. Well, whenever we see problems like this and we end up with grams of something, we normally get there from the moles of that same thing. So here, I want to start with moles to get to here. Now, if I have moles of sodium bicarbonate and they give me this information about the hydrochloric acid, I'm thinking they want me to calculate the moles of HCl. Now, for the moles of HCl, we have 123 milliliters. So we know that C times V should give me the moles of HCl, where V is the volume and C is the concentration. So what is the concentration of the acid? Well, here we have the pH is equal to 2.56, okay? So how does that help us get the mole of the concentration of the acid? Well, you have to remember that when you have a strong acid like HCl, it's going to be equal to the hydronium ion concentration because your strong acid behaves as follows. When it reacts with water. So if you start off with excess water and 10 of these and 0 of these and 0 of these, after the HCl has done its thing, this will still be in excess. You'll have 0 of these and 10 of these and 10 of these. Now, what if this were 1.0 molar and the rest of these were 0 molar? What would happen to the H3O? It would be 1.0 molar, and that would be 1.0 molar after it has reacted. Oh, and this shouldn't be OH. This should be Cl minus. My bad. So the point I'm trying to make is that whatever they tell you the concentration is of the acid, that's really going to be the concentration of the hydronium ion. So we know that the concentration of the hydronium ion can be found by taking 10 to the negative pH. Our pH is 2.56, so we get 10 to the negative 2.56. And so let's see what we get here. Now, the thing we need to remember is that the number of significant figures in the concentration is equal to the number of digits after the decimal in the pH. So we get 2 zig figs for this particular problem right here. So I'm going to do 10 caret negative 2.56, and I get 0.00275 molarity. So that's the molarity of the hydronium ion concentration, which is the molarity of the HCl. So using this pathway, here's how I would proceed. We know that we have 125 milliliters of HCl times 1 liter of HCl per 1,000 milliliters of HCl times the concentration of 0.00275 moles of HCl per 1 liter of HCl, and then times 1 mole of sodium bicarbonate per 1 mole of HCl. And then to get the grams, we need the molar mass of this stuff, which is 22.99 plus 1.01, which is 24.00, plus 60.01, which is 94.01. I believe. You can double check that. Okay. So let's see what we get for our estimate. 94 will go into that 10 times. 10 will go into that 12 times. 12 times this is going to be like 13 times 0.003. 13 times 0.003 is going to be like 0.039. So let's see what we get. 125 times 0.00275 times 94.01 divided by 1,000, and we get 0.032 of sodium bicarbonate. And so I'd expect to see this kind of work for this problem. I'd expect to see this kind of work for this problem. Okay. Let's see. I'm getting kind of tired of doing these. Let's see how many more we have. 1, 2, only 2 more problems. I'm going to grit my teeth and keep going. All right. So we have a solution of hydrochloric acid has a volume of 250 mils. You know what? This is a problem in your homework. So we're going to skip that one. And there really is only one more to do. Let's see if this one is interesting. In most states, a person will receive a DWI, driving while intoxicated, if the blood alcohol level is 80 milligrams per deciliter of blood or higher. Suppose a person is found to have a BAL of 0.33 moles of ethanol per liter of blood. Will the person receive a DWI? So we have 0.033 mole of ethanol. A very common abbreviation for ethanol in chemistry is ET, ETOH. Per 1 liter of blood. Now, what we need to do is compare this to 80 milligrams per deciliter of blood. So we want to turn this into milligrams. So we're going to go from moles of ethanol to grams of ethanol to milligrams of ethanol. For the liter of blood, we want deciliters, so we're going to go straight from liters of blood to deciliters of blood. Okay, and we don't have to do this as two separate problems. We can just do it as one. And we need the molar mass of ethanol. The molar mass of ethanol, there are 2 carbons, 24.02, 6 hydrogens, 6.06, and 1 oxygen. When we add these all up together, we get, let's see, that's 46.08 grams. We also need to know that 1 deciliter of blood is equal to 1 times 10 to the minus 1 liters of blood. And the way I got this is I just substituted 10 to the minus 1 for deciliter. Maybe you already know that there are 10 deciliters of blood in 1 liter of blood. These two conversions are the same thing. Okay, and we already know about the 1,000 milligrams is 1 gram. So let's start off with our 0.033 mole of ethanol right here, and our 1 liter of blood right here. So I'm going to take care of the blood first and multiply by 1 liter of blood per 10 deciliters of blood. So the liters of blood cancel, and we will have deciliters of blood. For the ethanol, we know the molar mass is 46.08, so 46.08 grams of ethanol per 1 mole of ethanol. And the moles of ethanol now cancel. And we know that there are 1,000 milligrams of ethanol per 1 gram of ethanol. And the grams of ethanol cancel. Boop. So we're going to be left with milligrams of ethanol per deciliter of blood. And of course, the reason we wanted that is so we could compare it to that 80 milligrams per deciliter. So I'm going to estimate my answer. Oh, and this should be times, not equal. So 10 goes into 1,000 100 times. 100 times 0.033 is 3.3. 3.3 times 46, my, that's got to be like 150 or so. This person is definitely DWI. 0.033 times 46.08 times 1,000 divided by 10, and we get 152. We only get 2 zig figs though, so 150 milligrams of ethanol per deciliter of blood. Yeah, the person is DWI because 150 is greater than 80. Okay, so this person will get a DWI ticket. They'll take it to court and they'll lose. They're almost twice the DWI. I don't know what is worse, DWI or DUI, driving under the influence. I have a feeling that intoxicated is worse. So here, this person is driving at almost twice the level of intoxication. which means that they might very well cause an accident. All right. Okay. That's it. Those are the problems that I have written up and prepared for this chapter. Chapter for Module 5 has already been posted, most of it. And hopefully you will be tuning in next week on Monday. Have a good day.